Hello students, Dr. Hines here and welcome back. Thanks for joining me. So in the previous lecture 1.1 we talked about the center of mass and how that can be used to reduce a lot of calculations for mechanics. However, today what I want to do is expand on how that can actually be useful. So today we're talking about toppling and stability. Hey guys, and welcome back. So one of the useful applications of center of mass is to determine the stability of an object. So what do we mean by stability? What we really mean is how stable it is in its ability to withstand forces, not topple over. Right? So let's say, for example, we're looking at a car going around a sharp corner on a steep hill. At what speed, at what angle would that car actually turn over onto itself, right? And of course, you may well know that a lot of the racing cars, they're shorter and stubbier to give them a lower center of gravity, lower center of mass, which gives them more stability. And of course, if you had like a big truck or like the car I used to drive when I was back in high school, it was very tall and narrow, it could be more at risk of toppling as we go around a corner. It also lets us know, like from a building standpoint, can this object withstand a side force, right? How much wind can it take, right? At what angle could we set our building up so that it wouldn't, I don't know why you do that, but at what angle could we set our building up so it won't fall down? And then again, that leads us to the next thing, which is of course the engineering application. The design point is, how can we design these things to either A, not withstand that, or what are my design criteria limits? All right, so let's talk about topple limit for a second. So figure A below shows a simple object with its center of mass noted by a red dot. The red line extending down, that's really just the force of gravity on that. So what you notice is that in the second figure, what we started to do is we started to tip this object over at angle theta, right? At the moment where that red line hits the edge of the object, that is the point where it is, in theory, if you could get it to stay there, it would actually stay balanced, right? Now we know that's very difficult, right? Try balancing a penny or something like that. It's just very difficult. But the point is, that point is what we call theta t, which is the toppling limit. If the angle of tipping is increased any farther, that object will continue to fall over, right? So again, what you notice is that that line of gravity, as the line of gravity extends over the outer edge, it's going to fall over. Okay, and that's what leads us to toppling here, right? So we will topple if the center of mass goes outside the outside edge. And if it's inside, then it will continue to fall back into itself, okay? So what we need to be able to do to actually apply this knowledge is be able to determine the topple limit. Okay, so let's look at this example here where we have functionally you guys can look at this like if a building looked like this, that would probably not be the best design, but you do see designs like this in cranes, for example, right? So let's go ahead and solve this, kind of look at what our topple point would be. But in order to do that, we of course need to do what we learned in the last lecture, which is apply the center of mass. So I've broken this down now to be two rectangles, and I've shown the center of mass of each one of those with a red dot. Okay, the first rectangle has an area of 27 and a center of mass at 5.5, 4.5. That's the green one, right? And then the top rectangle, the red one, has an area of 18 and a center of mass at 7.5 and 10. All right, those are the coordinates, right? So first we have to find the center of the mass, which we do using the equations we learned last time. So let's look at the x-coordinate, which is 27, the mass of the object, times 5.5, which is its x location, plus 18, the mass of the top rectangle at 7.5, and then you divide that, of course, by 27 plus 18, and we find 6.3. We then find the y-coordinates using the same procedure, going through, just using the different y-coordinates, which is 4.5 and 10, same masses, and we actually find 6.7. Okay, so our center of mass very clearly here is located at 6.3, 6.7. All right, so why does that matter? Well, it's because of this, right? So we just have to use a little bit of trig here, right, to find our angle, right? Remember, our angles move in. We have a 90-degree angle, so we start drawing our triangles, okay? So the rightmost point of contact, right, so let's go back one. The rightmost point of contact is located at x7, okay? So that allows us to, using trig, basically create our triangle. Okay, and of course remember that theta moves in because it's equivalent triangles. So if we just use the inverse tangent, putting 0.7 over 6.7, right, 0.7 being the difference between 7.0 and 6.3, and then the opposite side being the 6.7 from our original height, what we find is that our topple point is 5.99 degrees, so just about 6 degrees. So in this direction, right, this direction here, toppling over on the long edge, we could only tip the object 6 degrees before it actually started to fall over. Now I want you to ask yourself the question, with the design of this building, if we were going the other direction, would you expect that topple point to be higher, or would you expect the topple angle to be higher or lower? And then functionally, why? Okay, so again, let's look at a relevant example, which we had alluded to in the previous lecture, which is, let's think about a poorly packed truck. In this case, how much of an angle, like if they were going up a hill or if they were going around a corner and tipping, at what point would the truck continue to tip over on its side versus staying stable on the ground? Okay, so of course what we would do here is we would just draw our line. We would find center of mass, we'd draw a line down. Once it hits the outside edge of the wheel, as soon as it crosses that, the truck would fall over. And then you of course can, I mean in this case, obviously I'm going an extreme example. This truck's very poorly packed because we're putting it all on one side, right? How could we pack the truck better? How could we design the truck better with a wider base, right? And then you start applying this to other design examples like our buildings and the cars, which we talked about earlier. Okay, so just relatively simple concept, but it does kind of bring center of mass into focus as to how it's relevant to mechanics in general. So that is it for today's lecture. If you guys have any questions, make sure to leave it in comments below or reach out to me personally. Nothing else. Thanks for joining me.